a new chapter, chapter 5, and the first section is called Eigenvalues and Eigenvectors. So this word eigen is actually a German word, and it means self, and it's pronounced eigen. And somehow this name has slipped into mathematical jargon, and so we nowadays call this eigenvalues and eigenvectors. Okay. So what are they? Okay. So what we're dealing with is again a matrix, and we will deal again with a square matrix. So, but let me just remind you in general what happens when you have an n by n matrix. You can think of a matrix. Matrix has many purposes, right? It can be the matrix of the system of equations, the coefficient of the system of equations, but it can also be what we called a transformation, a linear transformation that we denoted T of A. And how did it work was very simple. You take a vector here, and then you multiply with A, and you get another vector of the same size because they're a square matrix. And this was what we called a linear transformation. Okay, and any linear transformation was given by a matrix. So there was same thing. And then in general, of course, what does linear transformation do? You have a certain vector here, say this is vector u, and then the linear transformation would give you a blue vector that might be totally different size, different direction. So this would be T of u, which is nothing else. Okay, it's a fancy way of just saying AU. Okay, I draw a 2x2 picture, but of course it can work for any. All right. So that's what a general thing does. I want to remind you, it's not for now, but just it's good always to remind you that we already talked about a special case here, namely, what if this image, the blue guy, is actually the zero vector? And that we called the kernel. So the kernel of this transformation, there were all the vectors u, so that AU equals 0. So that this blue vector is the zero vector. Okay, that's possible, right? And in fact, what does that mean? Well, if you think of this as a coefficient matrix of linear system of equations, that means that you're looking for the solution space, which we also call the null space of A. Okay, so there's another connection with something that we discussed last time. Okay, but now we're not going to be interested in a null space. That was from previous section. Now we're going to be interested in a different type of behavior. What if the blue vector is not a zero vector, but in general you see the picture, it could be anywhere, but I want it to be in the same direction as you. So not necessarily equal to it, but in the same direction. So that's what we're going to call an eigenvector. So an eigenvector U means that if I take the image on this transformation, in other words, if I multiply with my matrix, I don't necessarily expect it to be equal to u, but it should be in the same direction, which means what? A multiple of u. And now the multiple that we're going to use is we're going to use this Greek letter lambda. So this is a lambda. Greek lambda. It's very, book does it, and many places use this. So we have a vector, eigenvector is a vector so that the image of u under this matrix is a multiple. So this would mean in this particular case that the blue vector would not be this one, but be something like this. So this would be lambda times u. Now notice that lambda could be negative, and therefore the vector could be pointing the other direction. Okay, that's what negative do. So remember, multiplying with a scalar, so lambda is a scalar, right? We call that a scalar, which just means a real number. 2, 5, 6.3, 1/4, minus 17, whatever number you want. That's what this lambda is. And the scaling factor is the scaling factor, right? Okay, so moreover, it has a name, this lambda then. Because this is very special. We'll see. Eigenvectors do exist. We will see that they always exist. And so the corresponding value for this lambda is what we call the eigenvalue. Now, I said eigenvectors exist, so now you think, oh my god, there are going to be a lot of different eigenvalues, and you'll see there will be not that many possibilities. There are a lot of eigenvectors. In fact, eigenvectors will form again what we call an eigenspace, a vector space, but that's for later. So okay, eigenvector. So that's the condition here. So let's look first at an example perhaps before we move on. And let's see here. We take the matrix. A is the matrix 3, 0, 8, 9, negative 1, and I claim that the vector u, which I'm going to write as a column vector, the vector 1, 2 is an eigenvector. How do we verify that? So we can say, is this a vector? So what we have to calculate is this AU. So that is 3, 0, 8, negative 1 times 1, 2. This is what? 3, remember we go through this row and through the row and then through the column and then start adding the products. So 3 times 1 plus 0, that's 3. And you say here now, 8 times 1 minus 1 times 2, that is 6. Now what do we need to do here? So let me get rid of these arrows here. What we need to show is that this vector that I have now, this 3, 6, is a multiple of the original one. So the question is, what's the multiple? Well, I hope you see, right? It's 3 times 1, 2. Okay? But it is special, right? I just want to show you, what about, V? So is this an eigenvector? Yes. What about 1, 1? Let's try that one. Okay? 3, 0, 8, negative 1, 1, 1. So I work this out. It is 3, and then an 8 minus 1 is 7. Is this a multiple of 1, 1? No, right? In order to get a 3, I should have taken 3 times this guy, but then I get a 3 in the bottom too, not a 7. So that you see, it's very special to be an eigenvector. So how do we find these things then? Yeah, and also, yeah. So what does this mean here? We have an eigenvalue now. So 3 is we not only find an eigenvector, but we also find a corresponding eigenvalue 3 here. And here, this was not, so let's scratch it out. Okay. How do we do this? How do we find these things? Okay, I'm giving it to you, you can check it, but if I don't give you, how are you going to find one? And so what is it? Let's think about what this actually means here. So if you look at this equation, what does it mean to multiply with a scalar? There is actually, you can think of multiplying with a scalar is the same as this thing. Let's look at this matrix. What is this for a matrix? Remember, En stands for the identity matrix. So that's the matrix 1, 1, 1, and zeros here, right? And if I now multiply a matrix with a scalar, it means every entry, but of course there's only non-zero entries in the diagonal here, and everything else is 0. So we get a so-called diagonal matrix, but much stronger, right? It's a diagonal matrix, but everything is lambda. Okay, so what we do is now, so that's and what I'm trying to say is, if I take the matrix 3, 0, 0, 3, and I multiply 1, 2 with it, what do I get? I get 3, 6, right? So multiplying with a scalar is the same as multiplying with the corresponding multiple of the identity matrix. Why am I saying that? Okay, so I want to write this equation here as said lambda u, but I can think of this as actually this matrix, the matrix lambda times En u. So let's bring both to the other side. So there's A minus lambda, sorry, let me do it not too quick. AU minus lambda En u equals 0, right? So what we have is that A minus lambda En u is 0. Okay. Okay, so why this is not something we're going to do all the time, but I'm trying to get now to a conclusion. What is it that we have? So remember, I said an eigenvector is a vector so that if you take the image under the transformation, you get a multiple of it. Now there is a very obvious guy that always has this property, namely the zero vector. If you take the zero vector, A times the zero vector is the zero vector. So the zero vector is always an eigenvector. So we're going to exclude that case. So we're going to look at non-zero eigenvectors. Okay? Otherwise it's too trivial. Okay, so now, so what we're saying here is we have an equation here that we have to find this u is a non-zero solution to this system of equations. Now let's remember what this means. If you have an homogeneous system of equations, how many solutions does it have? Well, it depends, right? The two things. When you take its row-reduced form, if the reduced echelon form of this matrix can be either the identity matrix, in case and then the original matrix was invertible, but that means that everything is pivots. That means there is only one unique solution, right? Namely the zero solution. That's not the case. We don't want that. So the matrix, this matrix here, this is a new matrix, right? This matrix cannot be invertible. If I want to have a U, then this particular value of lambda has to have the property that the matrix that I get is not an invertible matrix. Let's look at the example that we had. So we had the matrix. What matrix is this? This might be a bit weird now at the moment, okay? So in our example 8, A was 3, 0, 8, negative 1. And we said that this was an eigenvalue. So let's subtract the matrix 3, 0, 0, 3 from it. That is this matrix, right? This is lambda En. Remember, as I showed you here, that's what it is, right? This is this matrix. What does this matrix look like? That's the matrix. Remember how you subtract is entry by entry, right? 3 minus 3, that's 0, 0, 8, and minus 4. And it's not so hard to see that this is a matrix with determinant 0, right? What's the determinant of the 0? The determinant of this matrix is 0. So yes, this is a not invertible matrix. The original matrix, by the way, is invertible. What's the determinant of the original matrix? Negative 3, right? Okay. So, okay. All this is, you don't need to do what I've said now. I'm just trying to introduce it now, but I'm going to recap what I've said. To get an eigenvector, we have to find a non-zero solution to a system of equations of this type. And this means that this matrix, so the condition for lambda to be an eigenvalue, so although we are interested perhaps in eigenvectors, we're going to concentrate first on eigenvalues. For lambda to be an eigenvalue is that this matrix has a non-zero solution. It means that the determinant of this A minus lambda En is 0. Let's do this on the example that we had. So we had the matrix 3, 0, 8, negative 1. Okay? That's the matrix A. Let's write down what this matrix is. A minus lambda En. Now, this lambda En, don't get bogged down by this fancy notation. It really just means this. You take the original matrix and subtract lambda from the diagonal. That's the only thing you need to do. That's how and we'll do more examples to get used to it. Okay? That's what this new matrix means. And this is the matrix we need to calculate the determinant of. We want the determinant to be 0. So in this case, we can find out what the determinant is, right? What is the determinant? The determinant of 3 minus lambda 0, 8 minus 1 minus lambda is, well, we use the formula. It's the product of the diagonal elements, 3 minus lambda times minus 1 minus lambda, minus the product of the antidiagonal, which is 0. Okay, so it is actually 3 minus lambda times, I want to write it, it's a bit weird to write lambda in the back, so I make it a little bit nicer to, I factor out the negative here and I multiply the negative there. Okay, why do I do this? Well, no. Okay, let me know. So I said the condition is that this is 0. So this has to be equal to 0. So what we get is a quadratic equation. That's basically what I said in this case. Quadratic, why? Because we start by a 2 by 2 matrix. If you would do a 3 by 3 or 4 by 4, you're going to get more diagonal elements, so higher degrees. Okay. And so we have to solve this. So let's solve this. So, and as I said, therefore, it's easier to bring the negative sign out here, and then you can write this as negative 3 times lambda plus 1. I hope you see that. Okay. And therefore, so we solve this is the two solutions are lambda is 3 and lambda is negative 1. Now we already noticed that lambda was 3 was an eigenvector. What about lambda is negative 1? Well, let's see what happens if I do this. So now we look at the eigenvalue lambda is -1. Okay, so what it means, I'm now going to plug in lambda -1 in this matrix. So what do I get? So I get 3 minus minus 1, 0, 8, minus 1, minus minus 1. So there's a lot of minuses here. Right? Okay. So that's the matrix. Let's write down 4, 0, 8, plus 0. Okay. So the claim is so what I'm saying, so we calculated this matrix here, and we have to now we have to now actually find a solution of this matrix, a non-trivial solution, an element in the null space. Remember, I'm throwing these words that you get used to them. So okay, so I have to basically solve the system equations with this matrix. Okay, so how do we do that? We're going to row reduce. We have to row reduce this guy with, if you want, the constant here are 0, so it's kind of not really necessary to do. The row operation we're going to do is, well, get first rid of this, the 4 here, right? So I get, copy it now quickly, it's 1, 0, 8, 0, 0, 0. So then the next row operation is row 2 minus 8 times row 1. That gives 1, 0, 0 there, 0 there, and 0 there. A lot of zeros, that's good. Because what do we need? Remember, for a matrix not to be invertible, and we know it's not invertible because we chose it. This is what we chose. The lambdas, these are the values for lambda that makes this matrix not invertible. Okay? That means that there must be a free variable. And you see that. We have one pivot and one free variable. So now we can solve for this thing, right? So this is, if you think of this as x1 and x2, you see that x1 is equal to 0 and x2 is equal to itself. Remember, the free variables, so perhaps better to write it this way, right? x1, x2, x1 is 0 and x2 is just itself. We always use the free variables here in case you get a little bit. So this is my free variable. So, and the free variables, all the other variables are in terms of the free variable. So x1 in terms of a free variable, but of course it's 0. Okay. So that means what? Okay. The basis of the null space of this matrix, we get this by factoring out x2. So this is a basis of the null space of this matrix. But we said what is an element in the null space of such a matrix? That is exactly an eigenvector. So this is the eigenvector. Or an eigenvector, say, not the an eigenvector. That corresponds to the eigenvalue -1. All right, I'll do another example, don't worry, then you perhaps get it better. Yeah, let me do another example perhaps. I'll take, it gets harder of course the bigger the size of your matrix is. So, okay, let's do this. So here is the matrix A, 0, 1, 0, 0, 0, 1, 4, -6, 17, 8. Now it looks rather innocent, but unfortunately it's not that innocent anymore. So here are the steps. Step 1. So the question, okay, what we're asking is what are the eigenvalues and give for each eigenvalue a corresponding eigenvector. Okay, so step 1. Step 1 is to get to this equation that we were talking about. Okay, this equation here, determinant of this matrix. Now, there's a choice that we have made, and perhaps I should have from the start done the opposite choice. Whether this matrix is invertible or it's negative, that's the same thing, right? So it's somehow easier sometimes to work with this matrix, and that's what the book does. I prefer to work with the matrix that I have started with. So you have a bit of choice. You can work with either one. And yeah. This is easier to work with, but this is somehow gives you the correct answer. That's the problem a little bit. And so I'm going to be a little bit off here with what the book does, because I think I'm going to stick to the one that works easier for. So step one is this equation that we had written down, a minus lambda e3, of course, here, right, is 0. The solutions to this equation will be what we call the eigenvalues. So the solutions are the eigenvalues. These will be the possible values for which this can happen. This equation has a name and is called the characteristic equation. I'm not entirely correct when I say this, because in fact the way I chose it, it's not exactly the characteristic equation, but it comes down to the same thing. So let's not really worry about what that is. So let's write down the characteristic equation. What does that mean? Okay, you take the matrix 0, 1, 0, 0, 0, 1, 4, negative 17, and 8, and then you just subtract lambda. So minus lambda from the diagonal, only from the diagonal. Okay, so let's see what we get. I get minus lambda 1, 0, 0 minus lambda 1, 4, negative 17, 8 minus lambda. Okay, now this really gets a little bit harder now, because we have to find this determinant, and there are lambdas in there, right? And you could do different techniques here to find this determinant. Let's try to do the way that we have been taught to do it is doing by row reduction. Now there's no good pivot in the first row, but there's a good pivot in the second row, in the first column, there's one in the second column, but then there are two non-zero elements. I prefer to work with this guy here. And so what I mean to say is I want to make this the pivot into this column here. So in other words, I have to get rid of this guy. But notice that this involves now a row operation. What do I have to do? I have to take row 3. I have to replace row 3 by, what do I have to subtract from there? Well, this quantity, right? So I have to do 8 minus lambda times row 2. That's what it is. There's nothing we can do about that. Okay, so let's see what we get. Minus lambda 1, 0, 0 minus lambda 1. Okay, and so now we have to multiply this with minus 8. So perhaps better to say multiply this with lambda minus 8. That's the negative this guy, right? And add it to the other one. Okay, so 0 times, that's nothing, so you get just 4. Now we have minus lambda, so minus 17. And to that we have to add this product. Minus lambda times lambda minus 8. And then also we do it here, but of course that should go with the 0. Good. So, determinant, we have to think, we're going to do column 3 expansion, right? But we have to do plus, minus, so it's going to be a minus, although this is actually not relevant, but we want to be correct. Okay, so we can scratch this out, and we find minus lambda 1, 4, minus 17, minus, let's expand this, minus lambda squared plus 8 lambda. And now it's a 2 by 2, which I can do much quicker, minus, and so we do minus lambda times minus 17 minus lambda squared plus 8 lambda, this product, minus this product. Okay, and let's work all this out. I'm going to keep my minus sign outside, so we get, I'm going to expand this. Okay, so minus minus is 17 lambda, minus minus, so plus lambda cube, minus 8 lambda square, minus 4. And this has to be equal to 0. That's, remember, we put this equal to 0 to get the characteristic equation. And you see, we get an equation of degree 3 here. In 2 by 2, we get a quadratic. In 3 by 3, we get a cubic. Okay? So this has to be equal to 0. The negative sign doesn't really matter now. And it's perhaps better to write this now in descending degrees. Okay, but yeah, what do you do now? We have to solve this equation, and solving equations is not easy. You might have actually been misled by all the problems that you've been doing in the previous sections of mathematics. Is that you thought, oh, okay, it is always, we can always find the method, but in general, it's very hard to solve an equation. And there are formulas, but very, very complicated formulas for these cubics. So we have one resource though, and that is to try to test for solutions. If there's a nice solution, then that solution should be divisible, should divide -4. I'm not guaranteeing that there is one, but of course I'm not going to ask you something where it's not the case. So we have to look at for possibilities of all the divisors of -4. That's unfortunately still quite a lot. That's plus or minus 1, plus or minus 2, and plus or minus 4. So all these 6 I have to test one by one whether they are zeros or not. It's a little bit cumbersome to test them all, and I'm not going to do this here. I know the answer. It turns out that lambda is 4 is a solution. So this one, so let me circle it, the plus 4 happens to be a solution. Okay, that's 64 minus 8 times 16, that is 60, no, that's 128, plus 4 times 17, that is blah, 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 68, minus 4. And that happens to be 0. Okay, so it's already not simple to find this 4, right? It's 6 things you fill in, and it's kind of a messy thing. I promise you, I'll never give you as complicated as this, but I just wanted to show you this is how things can work, okay? So that's how we find the characteristic equation. And then we can define the eigenvalues. We have to solve this. So what happens now if we have an eigenvalue? This means that lambda minus 4, this 4, is a factor. So we can factor this thing, let me get rid of this. We can factor this equation as lambda minus 4 times a quadratic. And so what is the remainder by the division? We have to do long division. Oh my god, okay, I know. But I promise you, I'm going to give you examples. I'm trying to give you examples, although the homework problems sometimes are more complicated. But examples where you don't have to do all this, where things are a little bit easier. But okay, if you do long division, and again, I'm not going to do the long division here myself, you find, so after long division, okay, the reason I don't want to do long division is because I'm used to do it another way, and so I never remember anymore where goes what. So I have to ask you, but you cannot answer me because you're sitting at home locked down. Okay, so all right, so after you do this, you actually factor this one. So after long division, you get this. I'm not explaining how this works, but please go look that up, how this works, okay? Is 0. So, and now this is quadratic. You try to factor the quadratic, and in fact, you see it's not possible. Two numbers that multiply to 1 and add up to -4 doesn't work. So what do you do then? Well, we have the quadratic formula. Okay, that one I'll tell you. Minus b plus minus square root b squared minus 4ac over 2a. So in this case, what we have, so lambda would be minus b. So here b is -4, right? A is 1 and c is 1. Okay, so we have 4 plus minus 4 squared, that's 16, minus 4ac minus 4 divided by 2. So there is this 4 plus minus the square root of 12 divided by 2. Square root of 12, I can factor out a 4. It's 4 times 3, right? 12. So I never bring that out. I get 4 plus or minus 2 times radical 3 divided by 2. So it's 2 plus or minus radical 3. There are the solutions. So the answer is the eigenvalues of this matrix are 4, 2 plus radical 3, and 2 minus radical 3. Okay, now, what does this mean? This means that for these three values, and only for these values, if you take this matrix here, this matrix, the one with the lambdas in, this one here, and you so this matrix, and you plug in either one of these values, 3 values, then you get a matrix whose determinant is non-zero. All the other cases determinant is 0, and so when the determinant is non-zero, there are more solutions, therefore there is a non-zero solution, therefore there is an eigenvector. Now we could try to find what this eigenvector is. It's very difficult, of course, if you have to work with values that contain a radical, so I'm only going to do it for lambda is 4. Okay, so lambda equals 4. So what I want is, give me an eigenvector for the corresponding eigenvalue lambda. So what we do, we plug in 4 in this formula. So we put lambda equals 4 in here. So this would be what? Okay, this is going to be, I'm going to have to erase things, otherwise I'm going to mess up. Okay. All right, so I'm going to put lambda equals 4 in here. What do we get? Well, let me write it as a matrix now. Minus 4, 1, 0, 0, negative 4, 1, 4, negative c, 17, and 8 minus 4 is 4. And now we're going to have to reduce this matrix. Unfortunately, it's, as I said, it's not a great example that they gave us here. But okay, let's just, it's good to once in a while see. I promise you get better examples. We need a pivot, and well, there's not really one there. Nothing is really nice, so I'm going to have to divide row 1 by negative 4. And so what I get is the matrix, I'm going to write it here, 1, minus 1/4, 0, 0, negative 4, 1, and 4, negative 17, 4. Next one is I'm going to use this pivot to make this 0. By the way, if you don't insist to get your pivots to be 1, you could already have made this a 0, this one a 0 by just adding these rows. But I prefer to work systematically. It's better to work systematically. So the row operation I'm going to do here is row 3 minus 4 times row 1. Okay, so what we get? First 2 rows are just copied. Okay, so negative, we multiply this with negative 4 and then add up to there. That is a negative 4, that's a 1 is minus 7, is minus 16. And then 4. Good. So, I need another pivot. This is not a pivot. Next one, I need to do the same thing. I'm going to again divide row 2 by minus 1/4, row 2. So I'm going to write it out what it is. So this is the result here would be 1 minus 1/4, 0, 0, 1 minus 1/4. Now I divided this row by negative 4. And here I have 0, negative 16, 4. I could have divided that row by 4, but that's an unnecessary step because now I'm going to use my pivot to get this 0. So what I'm going to do is sorry, I get a space here. What I want to do is the row operation, sorry, that I want to do is row 3, replace that by row 3 plus 16 times row 2, right? Okay, and that will give me 1 minus 1/4, 0, 0, 1 minus 1/4, 0. If I multiply this with 16 and add up, then I get 0 there, and 16 minus 1/4, that is minus 4 plus 4, that's 0. Of course, that's what has to happen. In other words, saying that not everything is pivot means that there is going to be a 0 row. So this tells me, yes, I'm right. This is going to be an eigenvalue. This lambda is 4. If I don't get a free variable here, so the free variable is going to be this guy, right? So this is going to be the free variable. So this x3 is free. To get actually the formula, I have to get a 0 on top of here. So let's do that. So one more row operation, right? So that is row 1, replace that by, what do we do? Add 1/4, sorry. So 2 row 1 at 1/4 times row 2. Okay, and what do we get? So I'll do it here. 1, and I'm multiplying this 1/4 and add this up. 0, multiply with 1/4 is minus 1/16. 0, 1, minus 1/4, 0, 0, 0. Okay, these are my pivots, and I can write this now. X1 is, remember, this is X1, this is X2, and this is the free variable X3. Okay, so we solve for this system. Perhaps let's write, it's better to write it as a matrix, right? As a column, I mean. X1, X2, X3, what are they equal to? X1 is equal to, bring this to the other side, 1/16 X3, 1/4 X3, and of course X3 is just equal to itself. So we factor out X3, we find 1/16, 1/4, and 1. So here is our eigenvector. So the eigenvector is the vector that this column represents. If I write it as a vector, it would be this thing. Okay. And we can you can check now that this actually does the thing. If I multiply this matrix with that vector, I'll get a multiple of that vector, and actually more precisely, what multiple? I get 4 times this vector, right? Now this is not the only one, because look, I can choose whatever x3 is. Of course, x3 0 gives me the 0, which we never want. But any other value of x3 will also give me a solution, will also be an eigenvector. So that's what I said, there are going to be a lot of eigenvectors, but only a finite number of eigenvalues. Okay, the difference between vector and value, right? So in fact, in some sense, this is sometimes easy. It's a good thing that we can choose different things. This is perhaps annoying because of the fractions, but I can get rid of fractions because I can choose x3 to be whatever I want. So another choice. So what is the choice this choice, what is that? Corresponds to x3 equals 1. But another choice would be take x3 equal to 16. What do you get then? 16 times 1/16, so you get the vector 1, 4, 16. Much easier to write down. Okay? So we have that's sometimes an advantage of this method of eigenvectors, that you can choose a good multiple without any fractions. Okay, so I want to do a few simple examples, and then perhaps next time we'll do a bit more complicated examples. The 2 by 2 is not hard, okay, and so I'm going to do a 2 by 2 first, later, but I want to give you one other example here. Suppose we have a triangular matrix. And this time I can do an example. Let's take this example here. 0, 0, 1, 0, 2, 0, 0, 0, 0, 1, 3, and 0, 0, 0, 4. And this is an upper triangular matrix, right? Remember, this means anything below the diagonal is 0. Okay. Let's think about what the condition is. This is A. What's the characteristic equation? So, sorry, I kind of said step 1 and never said what step 2 was, right? Step 2 was, this was calculate the eigenvector. Sorry, I should have here step 2. That was step 2, right? I apologize, I should have pointed out. So step 1 is again to get the characteristic equation. That means the determinant of A minus lambda A4 in this case. But that's just a fancy way of just saying take this matrix and subtract lambda from the diagonal. You see that? Okay. That's so I repeat. In the book, they do the opposite. They call the characteristic equations this matrix. What's the difference is that one is the negative to the other, and therefore, instead of, if you work this way, all the elements in here would just have the opposite sign. I warn you that if you compare my notes with the book, that's this one thing that is off. But it doesn't matter because it's about determinants being 0 or not, and minus 0 is still 0, right? Okay. So let's not talk about this guy. Now, what's the determinant of a... There's still an upper triangular matrix, right? Because I didn't really do anything. I just changed the diagonal a little bit. So we know what the determinant is. Remember? Because it's already in pivot form. We can expand along the first column and then along the... Okay? And so what we find is just a product of the diagonal elements. And so we see here that this is now our equation. This is equal to 0. So what are the eigenvalues here? Well, the solutions to this equation, but it's already factored, so please use a factorization, right? You know the zero product property. If a product is 0, then one of the factors has to be 0. If this is 0, then lambda is 2. Or if this is 0, then lambda is 2. So that's the same thing. If this is 0, lambda is 1. And if this is 0, lambda is 4. So these are the 3 eigenvalues. I said it's a 4 by 4 matrix, so we're expecting 4 eigenvalues, but it is, one is counted twice. That can happen. Okay? Now, let's calculate, so step 2. Let's count the eigenvectors for eigenvectors that correspond to lambda is 2. Okay? So what do? We take this same matrix, here's the determinant, but okay, this matrix now, okay, so we now replace lambda by 2 in this matrix. So what we get is 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 2, 1 minus 2, that's negative 1, 3, and then 0, 0, 0, 4 minus 2 is 2. And what we need to do, well, remember, it always goes back to this original equation here, right? This is what we're trying to solve. Okay, this is now the matrix that we just got, and we have to solve this system. So we have to basically find the null space of this matrix. So the null space of this matrix. So in step 2, that's what you do. Step 1 is you find the values of lambda. In step 2, for each of them, but I don't want to do all of them, otherwise it gets a bit too long here. Do another example. So for each of them, then you calculate the corresponding null space if you replace lambda in the general matrix by the value that you just got, lambda 2 in this case. You can do the same for this. So exercise, homework, but I'm not gonna do it for this yourself, okay? So the null space. Okay, we know what to do. We have to find the pivot form. So notice that very often now in these kind of situations, you're gonna get weird matrices, right? With a lot of zeros in it, which is good, of course. So where is our first pivot? Nothing in the first column, not in the second column. The first pivot will only happen here, okay? It's a negative 1. We should bring it on top, and I should also change it. I'm not supposed to do this, but otherwise it takes forever. So I'm replacing these two, and then I'm replacing row 1 by negative row. Yeah, what should I say now? So let me say it this way. I'm cheating slightly here, but okay. Allez. So what I'm saying is I'm switching the two rows, but in the meantime switch the signs. So get 0, 0, 1, negative 3, that's the switching of the signs. Okay, I don't want the zeros, this row 2, I'm going to bring all the way in the bottom, so I'm replacing it. Yeah. If I write down what the row operations are, it gets a bit messy here. So let me not do that. I hope it's clear what I'm doing. I'm going to move this guy all the way in the back, because it's a 0 row. I move this way all the way up, but I change the sign in the meantime. You're not supposed to be doing these things, really, and then the other two doesn't matter in which order we write them. You have to be careful let me say, it is okay what I do here, nothing is wrong. I just want to warn you that when you're calculating things like a determinant, then switching of rows and so matters, right? If you're just doing row operations, it doesn't really matter, right? You can do them, just make sure that you don't do things that are intertwined. Okay, good. So we have our pivot, we have everything actually. This is our pivot, this is our pivot. Oh no, we need to make the next one 0, so here we go. So the row operation I have to do is row 3, replace that, right, minus 2 times row 2. So I get 0, 0, 1, negative 3, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. Of course, these zeros are no longer going to play, so I'm not going to write them anymore. I have my two pivots, but I need a null space. That means I need a row reduced form. Remember from the review from last time? Okay, so what we need to do is make this row reduced. So there's one more thing. I do row 1 plus 3 times row 2 to get a 0 here. And that is what I get, right? I get 0, 0, 1, 0, 0, 0, 0, 1, and the rest is zeros. So we have two pivots. Okay, so the pivots are, let's mark everything, right? The pivots, let's do them always in blue. That's x3 and x4. But the free variables are now x1 and x2. That can happen, right? Okay. So, and then the deal was, you write x1. No, sorry. No, not x1. Not the wrong. Let's do everything black. We write x1, x2, x3, x4 in terms of the free, the green variables. So x1 is of course just itself, x2 is just itself, x3 is equal, x3 is 0, right? This means x3 is 0, x4 is also 0. Okay, so that's what we get. And then to find actually a basis of the null space, let's go all the way. Let's find the basis of the null space. What we do is we factor out x1 and we factor out x2 and see what we left. We have two columns here. Well, one is 1, 0, 0, 0, and the other one is 0, 1, 0, 0. So this is a basis of the null space of this matrix that I obtained by plugging in lambda is 2. Now, what is this actually calculate? We will call, so this means that, what does it mean? Any vector in this null space is an eigenvector for the value lambda equals, lambda equals 2. And therefore we call this actually, this null space, so the null space of this was of the matrix A minus lambda En, right? We call the eigenspace of lambda. Right? For each lambda you get a matrix and you know that there is a null space, and the null space we call the eigenspace. And so we have now found a basis here. So 1, 0, 0 is an eigenvector, 0, 1, 0, 0 is an eigenvector, but any combination, any linear combination of these two is also 1. So it's therefore often enough to give a basis. And you could check, right? If you do, you could check what happens if you take this vector and you multiply it with this this matrix, you get exactly twice this vector. Okay, so I want to do one last example, which is simpler, and therefore I can work it out in full detail. Let's do this matrix, a 2 by 2 matrix. Okay, so step 1, the characteristic equation. That is the determinant. You take the matrix. At least that's what I do. In the book, as I said, I do just the opposite. And then subtract lambda from the diagonal. Now it's a 2 by 2. That's very quickly done. Oops, no. I want a determinant. That's minus 1 minus lambda, 3, 2 minus lambda, and that's minus 1 minus lambda times minus lambda. A lot of minus signs. Be very careful here. Minus 6. I hope you see that's how the formula gives you. So let's expand this. That is lambda plus lambda squared minus 6. So lambda squared plus lambda minus 6. And we have to put this equal to 0. That's the characteristic equation. And so the eigenvalues are now the solutions to this equation. So we have to factor this, and this time it's not so bad. Add up to 1, so I'm thinking plus 3 and negative 2 here. The product is negative 6. Okay. So we see the eigenvalues are lambda is negative 3 and lambda is 2. That are my eigenvalues. Okay. Step 2. Now I want to calculate the eigenspace. The eigenspace corresponding to each of these two solutions. Eigenspace of lambda equals -3. What do? I take this matrix and I plug in lambda equals -3. So what I get, let's see, I have just enough space to see it. -1 minus -3, so that is +3, that's 2, right? Then I have a 3 here, I get a 2, and -3 is 3, okay. And this matrix should have determined 0. I hope you see that this is the case. Okay, so row operation, well, yeah, it is again, I did a fraction here, so, okay, so row 1 divided by a half row 1, that's not so bad, right? I get 1, 3 halves, 2, 3. Now I can get my row operation, row 2 minus 2 times row 1, 1, 3 halves, that is a 0, and then minus 2, that's a 0 there. Okay, and that's the pivot form, right? Because this is now our pivot, that's the pivot, and this will be our free variable. So x1 and x1, x2 is the free variable. That's what I meant to say. So I can write down the solution. x1, x2 is equal to, x1 is equal to, well, this is the equation that tells me what x1 is equal to, is this minus 3 halves x2. Remember, this means x1 plus 3 halves x2 equals 0, right? So that's why I have to bring this to the other side, and that's why I get a negative here. Okay. And then x2 is just itself. We factor out x2, and we have minus 3 half, 1. So this is our eigenvector, or better even, that's even the basis of our eigenspace. So this is the eigenvector or a basis, even better. And again, perhaps because of the fraction here, I can make a better choice by taking x2 equal to 2, for instance, right? Then I get a nicer one without fractions. But let's not dwell on that now. Now this is the eigenspace for lambda is -3, but we should do this for all values, eigenvalues. There are only 2 here, so it's not that much work. Lambda is 2. What do we get then? So we now replace lambda is 2 in this matrix. And what do we get? -1 minus 2, that's -3. And I have a 3 then. And then here I get 2 and, what was my lambda? 2, right? 2, -2. Okay? This time I'm a little bit better luck. I can actually divide row 1 by -1/3. And I can actually divide row 2 by 2. Why not? Let's get rid of all big numbers. Well, they're not big, but okay. 1 minus 1 and 1 minus 1. Okay, and then the row operation is obvious, right? Row 2 minus row 1. By 2 of course, it goes very quickly, this kind of calculations. So, and the homeworks, I think, will be mostly 2x2s. So 1, -1, 0, 0. Again, we need to have a 0 row because we need to have a free variable, right? That's the whole point. So this is our pivot variable, and the other one is a free variable. So this is x2, and so let's write the solution now. x1, x2 is equal to, x1 is equal to, bring this to the other side, that was a plus x2, and x2 is just itself. So don't forget that. Sometimes people write 0 here because they think, oh, this is this row. No. x2 is equal to itself. It's these rows, these 0 rows never have anything to do with what happens, right? We have to look at the pivot rows. The pivot rows gives me the values for the pivot variables. What about the free variables? They are just themselves. Okay, so x2, 1, 1. And so this is the basis of our eigenspace corresponding to the value lambda equals 2. And that's how we solve these things. Okay, we're probably going to do a little bit more next time about this, and also I'm going to assign our homeworks for this.